My name is Matt Handley and I'm Product Manager for Mitsubishi Electric for variable speed drives. What I'm going to show you today is a simple but practical demonstration of how much energy you can save by fitting a VSD onto a fan or pump application. I'm sure by now you've seen in the media, you've read in the press, or other manufacturers have spoken to about the benefits of fitting VSD variable speed drive to fans and pumps. But I'm not convinced the message is still getting through. So with the aid of my demonstration, I will show you just how much energy you can save. I will also show you, if you configure the drive correctly, how you can save even more energy, a further 12%. So what we have here is our practical demonstration. This demonstration consists of two identical blow motors. One of these blow motors is controlled DOL or direct online. This means the motor is running at a constant speed and the flow is controlled by a mechanical valve. The other system we have fitted a variable speed drive to in place of the direct online starter, and this will control the speed of the motor electronically. So first of all, I will start the direct online motor. And next I will start the VSD controlled motor. From the HMI, I can read back the current, the voltage and the power from each system. So let's first take a look at the direct online motor. We can see that its current is 0.79.8 of an amp. The line volts are 408 volts, and these are measured from this meter connected to 3 CTs on the feed to the motor. If I now vary the flow on the direct online system using the mechanical damper valve, I then take a look back at the HMI, what I see is that the current and the voltage and therefore the power have remained the same. What I'm going to do now is I'm going to use the inverter drive to vary the speed of the motor on the second system electronically. Slowing the motor down will therefore reduce the flow. First of all, we can take a look at the inverter current, voltage and power, and we can see we have 0.75 of an amp and 415 volts, which is the same as the direct online system was at full speed. Okay, if I now reduce the speed of the inverter, what I'm going to do here is match the balls in the tube to mimic the same airflow. So with the flow the same in both tubes, I can now see that the DOL system is at 0.8 of an amp, 414 volts, whereas the frequency inverter reduced the speed, went out 0.34 of an amp, 147 volts, saving overall 110 watts. I'm now going to stop the VSD. I'm now going to enable the energy saving mode on the VSD. I'm now going to start the VSD system up again to match the balls in the tube. And what you can see now is that my voltage is reduced, my current is reduced, and I'm saving 10% more power. One final demonstration. I'm now going to run the VSD back at full speed again with energy saving on. So energy saving, as we see, is turned on. I now start the system. What I see with full flow is at 50 Hz I now have half the current and half the voltage I had before with energy mode disabled. If we take a look at the energy consumed by this setup, what we see is the power reduces with the flow. Variable torque loads are typical of centrifugal fans and pumps and have the largest energy saving potential. They are governed by the Affinity Laws, which describe the relationship between the speed and other variables. This law states that the change in flow varies in proportion to the change in speed. The change in head or pressure varies in proportion to the change in speed squared. The change in power, however, varies in proportion to the change in speed cubed. This power to speed relationship is also referred to as the cube law. When controlling the flow by reducing the speed of the fan or a pump, a relatively small speed change will result in a large reduction in power absorbed. In actual fact, this law determines, for example, that for a 20% reduction in speed, there is a 50% reduction in power consumed. So what we've seen today, using this simple but practical demonstration, is just how much energy you can save when fitting a VSD in place of a mechanical damper onto a fan or to a pump. We've seen that when we use the OEC, optimum excitation control, inside the inverter, we can then optimise this energy output even further, and we can save up to 12% in practical terms. What we've also seen is that when a motor is oversized for a system, that OEC, optimum excitation control, will compensate for this. We saw when I used this that on the inverter motor at full speed we were at half the current and half the voltage and vastly reduced power. This has other benefits, of course. If the motor is only getting just the amount of current and voltage it needs to rotate the shaft, therefore there is no wasted heat. And we have practical demonstrations here where we run an OEC motor versus a straightforward inverter controlled motor, and the skin temperature after 15 minutes is half. If you'd like to experiment with energy saving on fan and pump applications using the technology I've showed you today, please go to our virtual system online.